We've seen a few different universal constructions so far, but there are many more universal constructions. And I want to show you one example which is not a limit. It has nothing to do with a limit. I mean, some of the universal constructions were like really limits, like the product, co-product, right? So now we know that these were limits. But there are other constructions that have nothing to do with limits. And this construction is the construction of a free monoid. And it's a very interesting construction because it involves another category and plus it involves sets as well. So you probably remember, but I'll remind you what a monoid is, okay? So we had actually two definitions of a monoid. One is like set theoretical and the other was categorical, in which it's a category with a single object, right? And multiple morphisms. They are completely equivalent. So let me start with the set theoretical description, okay? So we have a set, let's call it M, right? And we have multiplication, sort of, you know, so we have some mapping, let's call it mu, that takes a pair of M and M and maps it into an M, right? So we pick pairs from the set, right? And we assign to them the product, which is another element in the same set, right? So it's picking pairs and assigning elements, right? And there is also one element, special element called unit. Let's call it E, such that E times anything equals anything times E equals anything, right? This anything, I mean, the same element, right? So this is the unit law. And the other thing that was necessary, so that's almost complete. Another thing is that it's associated. So A times B times C must be always equal to A times B times C. That's a definition of a monoid. Right? In fact, if we didn't impose these conditions, it would be called a magma. There's something called a magma. There's no additional conditions, just a binary operation. But monoids are everywhere. So we can think of this as a two-step process. This multiplication, right? Multiplication is like first we pick a pair. And then we assign to this pair an element of the set. And it could be that multiple pairs are assigned to the same element, right? So if you have like, you know, addition, right? A monoid of natural numbers with addition. So you would have 0 plus 3. It's the same as 1 plus 2. And it's the same as 2 plus 1, and it's the same as 3 plus 0, right? So we have this identification. These are different pairs. 0, 3, right? Let me write it as a pair 0, 3. This is a pair 1, 2. This is a pair 2, 1. This is a pair 3, 0, right? And they are all identified with 3, right? So 3 is equal to all of these things. Now, some of these identifications follow from the axioms, from the rules of monoid, right? So the fact that the pair 0, 3 and the pair 3, 0 are both equal to 3, that just follows from this guy, right? But this, like, you know, why is 0, 3 the same as 1, 2? Well, that's sort of accidental. That's something that's very specific to this particular monoid. So when we construct a free monoid, we try to separate these two things. We say, well, there is one thing, we have to identify certain pairs because of the laws of monoid. So these are mandatory, right? Mandatory laws. But there is also this additional stuff, you know, these accidental identifications. We don't care about these. Like, can we have a monoid in which we don't have any of this stuff, any other identifications? And that's called a free monoid. So the idea is that a free monoid will have no additional identifications other than enforced by the law. And any other monoid is sort of like, well, take the free monoid and just put additional identifications, these accidental identifications, that you'll get a different monoid. So like here you would say, okay, I have a free monoid, but now I'm identifying this with this, and this with this, you know, and this with this, okay? And I get some new monoid, right? My specific monoid of, let's say, natural numbers with addition. So let's see if we can like construct a free monoid, an example of a free monoid. So we would start with some set of generators. Okay, so we start with something. We start with, let's say, we have two generators, A and B. That's our set of generators. And now we are saying we want to construct a monoid that's based just on these two generators. What does it mean? Okay, so a monoid has to have a unit. Well, so let's add to this set E. Okay. Now let's start multiplying stuff. Okay, so what can we do? We can multiply E times A. We can multiply A times E. You know, E times B, B times E. Okay, these are boring, right? Because these all, by laws, will have to be identified with A, B, B, right? So our free construction will have to have this identification because we want this to be a monoid, right? But there are other possibilities like A times B and B times A. Okay? And we are saying A times B is not identified with anything else. Okay? A times B is not the same as A, it's not the same as B, it's not the same as E. It's a new thing. So we add the new thing, let's call it AB, and we add a new thing called BA. Okay? So we're just expanding this set by adding these pairs, right? Without doing any additional identification. So in the next generation, right, we'll go over this and do all the multiplication, right? So what are the new things, the new interesting things? Well, of course, E times AB and E times BA, we know what it is because of the laws. But there's also things like A times AB, right? B times AB, and then there is AB times A, and there's AB times B, okay? So, are these four new things? Not really, because we have also associativity. So, do we have BAB, for instance? BAB. Oh, I didn't have BA yet. Huh. Okay, so I have BA times A, BA times B, and so on. You see what I'm driving at? That BAB is the same as this guy, right? Because of associativity. So I have to identify certain things because of associativity at this level, right? after I've gone to the second generation, and so on. So it turns out that at this level, I will have to add things like AAB, oh, forgot. There's also AA, right? And BB, right? They are easy to forget, but A squared and B squared are also here, right? So here I'll be adding things like AAB, ABA, and so on. Okay? You see the pattern? Yes?
Why did you add AB and BA? Doesn't associativity make those the same?
No, that would be symmetry, right? Not all monoids have symmetry. You know, it's like if you do matrix multiplication, for instance, A times B is not the same as B times A, right? Okay, so if you look at this, you might recognize a pattern. Actually, I should write E in the beginning here instead of here, right? So this will go on forever. We'll be adding infinitely many of these things, right? No, associativity tells us, well, so these are just lists of these elements A and B in different combinations, right? Associativity means that I don't have to put parentheses there, right? So these are just all possible lists of A's and B's. Right? So a free monoid really is all possible lists of generators, right? And even, you know, if we want, we can say that E is an empty list, right? So if this is an empty list, this is a list that has A, this is a list that has B, you know, this is the list of AB, this is a list AA, and so on, right? AAB, and so on. So these are just all possible lists. It's like words in a language that has the alphabet A and B. Okay? We can pick generators, any set of generators. We could pick an infinite set of generators, for instance, integers, right? And we'll have, what? Lists of integers, right? So a free monoid whose generators are integers will be all possible lists of integers. And what's multiplication? Well, multiplication is just concatenation of these lists, right? And a neutral element is an empty list. So you concatenate an empty list, right? You get the same list. So that's what a free monoid is, okay? Now, there's just one problem with this, okay? We've been talking about elements and sets all the time, right? So this is wrong. This is wrong. Well, not totally wrong, but now that you know what it is on sets, let's put our category theory hat on. So, we need a category, right? Monoids should form a category. What's a category of monoids? Objects in the category of monoids will be monoids, obviously, right? But what are morphisms? So if we just take, okay, so a monoid is a set, right? Under the covers, it's a set. So if we take all possible functions between sets, we won't get a monoid category, we'll get a category set, right? So morphisms in a category of monoids have to be special. They have to understand the structure of these monoids. So a function that preserves a certain structure is universally called a homomorphism. And you'll see homomorphisms in many other areas, right? This is like the simplest, well, I don't know if this is the simplest, but a homomorphism that preserves monoidal structure. So it means it's a function that takes a monoid to a monoid, right? And what should it do? Well, it should, for instance, take the unit element in one monoid to the unit element in the other monoid, right? Because unit element is special, right? So if we have two monoids, this is E1 and this is E2, then a homomorphism H should take E1 to E2, right? Moreover, if we have, okay, I always draw them too small, right? If we have A and B, then homomorphism will take A to some HA, right? B to some HB. But now we can do multiplication here. We can have the AB, right? A times B. It's another element, potentially, right? What should this guy go to? Well, it will go to H of AB, right? But in this monoid, we can do the other multiplication. We can multiply AH times AHB, right? So if we want to preserve the multiplication, these two guys have to multiply to give me this, right? So the condition for this is H acting on E1 is E2, and H acting on A times B must be equal to H acting on A times H acting on B, right? Now this multiplication, maybe I should write dot 1 and this is dot 2, because this is multiplication in the first monoid, and this is a multiplication in the second monoid, which is a different multiplication, right? I mean, this could be a sum and this could be a product, for all I know, right? But the important thing is that homomorphisms preserve the structure of monoids, which means that if I have a category of monoids, right, the morphisms in this category of monoids, which will be the homomorphisms, will know stuff about the structure. So I can derive stuff about properties of monoids by just looking at morphisms. And that was like the whole idea of category theory, right? Don't look inside the object, look at morphisms. Morphisms will tell you everything you need to know. Okay, so, yes?
Can this thing be defined using like F algebra?
F algebra. Oh, F algebra. Yes, absolutely. Yes, you can use F algebra to define monoid. Well, in fact, monoids can be defined in so many different ways. You can have a monoidal category, you can have an F algebra, and so on. Monoids are everywhere. Okay? But this is just one particular way of doing this, right? So, monoidal category. Sorry. Category of monoids. Sorry, monoids. The category of monoids with these homomorphisms as morphisms. Is this really a category? So I haven't shown you that this is a category. What does it have to be? Identity, right? Identity morphism. Identity morphism should be like identity function. An identity function is a homomorphism. It takes a monoid into the same monoid, and it maps unit into unit, and maps product into product, right? So obviously identity works, composition. Well, this is like a simple function composition, and you can just follow. Okay, E maps into E here, and maps into E here, right? These two guys map into these two guys, this product will map into this product, this product. So, obviously it works. Associativity works. So it is a category. It's a beautiful category. So now I would like to say, let's forget about the origin of this category, that we had these sets, the ugly sets, right, and functions. Now we just have these points that are called monoids, and we have these homomorphisms that are, you know, and that's wishful thinking. Can't do that. Why can't I do that? Because I cannot define a free monoid this way. Because the construction of a free monoid started with a set. I said we need a set of generators, right? And that's a set. It's not a monoid. It's not a member of the monoid category. It's just a plain set. In order to make it into a monoid, I had to add the E, right? I had to add additional things, right? It was not a monoid, and it cannot be a monoid. So, what's the next best thing? The next best thing is find some kind of connection between set category and monoid category, right? Now, you might think, okay, well, maybe there is a functor from set to monoid, right? Well, cannot, because there are many monoids that correspond to the same set, right? They have different multiplication, but they have the same number of elements, right? So that won't work. However, the other way around does. So I can have a functor from category of monoids, which is called mon, right? So I can have a functor that takes monoids to set. And these sets are called the underlying set. So every monoid has an underlying set, right? This is how it was generated to begin with. It was created from a set, right? We tried to forget about this, and we sort of partially forgot, but now this memory is coming back to us, right? That there is an underlying set, okay? So there is a functor, U, from monoid to set, that assigns an underlying set to every monoid. Now, why is it called U? I don't know really, but the name for this functor, and it appears in all kinds of categories, is called forgetful functor, because it forgets. It forgets that there was a structure, right? It just says, well, it was a monoid, but really, I forgot about how to multiply things, and now it's just a set for me, right? So this is a name, forgetful functor, and usually the letter for this forgetful functor is U. So there is a forgetful functor from monoid to set. Okay, so we are getting somewhere, right? So for every monoid, you know, when we have a monoid M, we can always kind of project it into a set UM. So here's the monoid category up above in the clouds, and here's the down-to-earth set, okay? And we have this monoid. And there could be multiple monoids going into the same set. Fine, that's fine, right? And it's a functor, so like if you have a homomorphism between two monoids, right? Then we suddenly remember, oh, it was a function. We started with the function, right? So this is like, this is H, this is UH. It's just a function, right? Okay. So this is a function, but we know that this function, it's a good function. Like if we knew what a unit was in this set, but we don't, we forgot, right? If we knew that, it would map this unit into this unit, right? So So now, knowing this, we have to set up the universal construction to create this monoid. So we have to find like the best thing that would correspond to a given set of generators, right? So here, down here, in the category of sets, we have a set, let's call it X, okay? This set is our starting set of generators. We cannot define it in the monoid category, but we can define it here. We can pick any set and say this is our generators, right? So now we have to say what does it mean that a given monoid has these generators? What does it mean that it has these generators? Well, we kind of have to make an awkward statement here and just count on the fact that when we do universal construction, it will actually pick something that makes a lot of sense. But to first approximation, it's enough that we have a function here, let's call it p, from x to um, right? And this function, well, it kind of embeds the set x inside um, right? That's what a function does. It takes a set, puts it into another set, right? Now, this function might do weird things, like might collapse some of the stuff, right? Which we don't like, because we would like this set of generators to actually be mapped into a set of generators of this guy, right? So we don't want this stuff to be collapsed, right? Like if we have these two generators, A and B, we want UM to have A and B, right? We don't want to collapse. But as you know, universal construction will like unglue these things, right? It will pick the best one. It will say, oh, this is like ugly because it glues things together. I have a better one, right? So universal construction starts with a pattern, right? So the pattern here will be, well, we pick one set X and fix it, right? So this is fixed. But what will be changing is we pick a monoid M, and we pick a function P that goes from X to UM. Okay? So this is our pattern. And now look, this is like we had all these patterns when we were doing universal constructions. Here, the interesting thing is that a monoid is in one category, and X is in another category, right? So it's like an intercategorical pattern, but it's fine, you know. Nobody says that all parts of the pattern have to be in the same category. So we pick. So X is picked once and for all, right? This is our set of generators, and now we are looking for these patterns where we pick a monoid and a function P from X to the underlying set of the monoid, right? So we'll have lots of these things, right? So as we did before, you know, with every universal construction, we just have many instances of this pattern, right? Lots of different monoids and lots of different functions. All of them follow this pattern. So that was the first part of every universal construction, find the pattern, right? And it has to be like very rough pattern because it will be fine-tuned by the universal construction. The second part of the universal construction is to have some ranking of these matches, right? Because we want to pick the best one, right? So we have to rank them. So how do we rank these things? we will say that M is better than N. So here's some other guy, N. Another candidate, right? And we'll say that M is better than N if there is a morphism from M to N. It's called H, right? It's a homomorphism because now we are in the category of monoids. So these guys are homomorphisms, right? So here's another guy. This guy also has a projection here, UN, right? And since it's a pattern, right, it's a hit on our pattern, it will have a function from X, let's call it Q, right? So Q goes from X to UN. Right? So here's one pattern, P and M. Here's another pattern, Q and N. Right? Why is this one better? This one is better if there is a morphism H. And if you have a morphism H here, of course, since the forgetful functor is a functor, we'll have UH here, which is just a function. So there is a function UH from here. Now you see what's happening here? You see the triangle, the magic triangle? This triangle has to commute. Okay? So we will say that M is better than N if there is a morphism from M to N such that this triangle commutes. And this triangle is formed by dropping H to UH, right? And then connecting UH after P. So I will write it down. UH after P equals Q. Okay? That's the commutation condition. Right? So, how do we understand this? We understand this. So X is the set of generators. P picks these generators inside the monoid M, right? Q picks the same generators inside of this monoid, right? So this is a monoid homomorphism. It maps these, right? It maps these generators to these generators, right? So it's right. Maybe it collapses some of them. We don't care, but fine. But this is a commuting triangle. Okay, so now the final step in universal construction is say, okay, the universal monoid, the free monoid is the one that has a unique mapping to any other, right? So we had the ranking here, but now the best one of them, the free monoid, right? The free monoid is one that has a unique homomorphism to any other monoid, fulfilling these conditions, right? So what does it mean? Well, first of all, it will definitely, due to the Goldilocks principle, it will pick this P which doesn't collapse anything here, right? Q might collapse things, fine, but P will not, right? Because if P collapsed a few generators, then there would be another one that did not collapse and it would be better, right? So, now, what this says is that if we find the same generators in any other monoid, right? then what can happen is UH maps one monoid into another monoid, right? It's a homomorphism of monoids. Well, H is a homomorphism of monoids. So it will map generators into generators, products into products, unit into unit, right? But what it can do, it will spoil some things probably, right? Because these are not as good as this one. So how can it spoil? Well, first of all, this other monoid could be much bigger, right? So like, it will just inject our monoid into the bigger monoid. So that's fine. So that just means that the free monoid is like the minimum of stuff that is obtained through these generators. Like if we started with A and B, you know, free monoid will only have A and B and all the lists of A and B's, right? It will not have C or D, right? This other monoid can have C, D, E, F, and so on, right? So it will inject this monoid inside this other monoid, and it's fine, right? The other thing it can do is, even if these two monoids are the same size, right? Well, it might collapse certain elements, right? And this is exactly what I started with, saying, you know, every monoid can be obtained from the free monoid just by identifying certain pairs, right? So this guy will identify, will squish them, glue together, and so every monoid can be obtained this way. Okay? So, yes, that's it for today.